Today I'll be talking about carbocation, its formation, stability, and fate. We'll also cover the rearrangement of carbocations. Carbocations are important in organic chemistry. Although they cannot be isolated, we can understand the mechanisms of chemical reactions. So it's important to understand how carbocations are formed, the stability of different carbocations that are formed, and also what happens to the carbocation once it's formed. It can either undergo rearrangement, which is pretty quick since the rearrangements are intramolecular. They require less energy, and once the carbocation is rearranged to the most stable form, it can be trapped by a nucleophile, or it can lose a proton to form an alkene. That's a double bond. So let's take a look at a simple carbocation. This is the methyl carbocation. It has empty p orbital. This p orbital is perpendicular to CH bonds. All the CH bonds are in the same plane, and I've drawn this p orbital, which is empty. So the most important thing to remember is all carbocations do have an empty p orbital. Let's look how carbocations are formed. There are three ways carbocations can be formed. The first one is in a polar solvent. An example would be an alkyl sulfonate. In ethanol, will generate a secondary carbocation. In this case, haloalkanes also can generate carbocations in polar solvents. Another way to generate a carbocation is by reacting an alkene with an acid such as HCl. Let's take a look at this example. So this is an alkene. In aqueous sulfuric acid, it will get protonated and generate the carbocation. The third way to generate a carbocation is by reacting a secondary or a tertiary alcohol by an inorganic acid like sulfuric acid or HBr. So we have a tertiary alcohol right here. When it reacts with HBr, it will lose a molecule of water to generate the tertiary carbocation. So once the carbocations are generated, let's understand the stability of the different carbocations that can be generated and what happens once the carbocations are generated. So these are the different carbocations that can be generated. The first one is a primary carbocation because the positive charge is on the primary carbon. The second is its secondary carbocation, and then you have a tertiary carbocation. This is an allylic carbocation. The positive charge is next to a double bond, whereas in a benzylic cation, the positive charge is next to a benzene ring. To understand the stability of primary, secondary, and tertiary carbocations, we can think about hyperconjugation. So in a primary carbocation, if you recall, it has an empty p orbital, and this p orbital can overlap with the CH bond on the adjacent carbon. But that CH bond needs to be near parallel to the empty p orbital for the hyperconjugation to occur. So in case of primary carbocation, there is only one CH bond that can be parallel to the p orbital. In case of secondary carbocation, there are two CH bonds, one on this carbon atom and the other one on this carbon atom, that can overlap with the empty p orbital. In case of tertiary carbocation, you have three CH bonds that are near parallel. One on this carbon, the other one is on this carbon, and the third is on this carbon. So you can see that the hyperconjugation increases as we move from primary to secondary to tertiary. And so the stability of the carbocation increases, and tertiary carbocations are the most stable, and primary carbocations are the least stable. Let's look at allylic and benzylic carbocations. So allylic and benzylic carbocations, the positive charge is delocalized via resonance. In the case of allylic, it's delocalized in the double bond. In case of benzylic, the delocalization occurs in the benzene ring. Since the delocalization in benzene ring is much more as compared to a single double bond, so benzylic carbocations are very stable. So let's remember the order of carbocation stability. Primary carbocations are the least stable, benzylic carbocations are the most stable, and the carbocations are stabilized by delocalization of the positive charge via hyperconjugation or via resonance. Let's think about what happens to the carbocations after it's formed. So there are three things that can happen to a carbocation after it's formed. The first thing that happens is rearrangement to give a more stable carbocation. And this happens via a hydride shift or an alkyl shift. And the resulting carbocation is more stable because of relief of steric or ring strain, or it gets more stable due to hyperconjugation or resonance. Once the rearrangement is complete, then the carbocation will be trapped either by a nucleophile or will lose a proton to form a carbon-carbon double bond. Let's look at some examples where the rearranged carbocation is trapped by a nucleophile. The nucleophile can be an anion or it can be a neutral molecule. Let's start with a simple example. This is a tertiary alcohol. In presence of HBr, it will get protonated and then it will lose a molecule of water to form the tertiary carbocation. This tertiary carbocation will undergo rearrangement via hydride shift to give benzylic carbocation. Recall that benzylic carbocations are more stable than a tertiary carbocation because the positive charge in a benzylic carbocation can be delocalized in the benzene ring. The benzylic carbocation is then trapped by a nucleophile to give you the product. Let's look at another example. This is a secondary alkyl sulfonate in ethanol. It will generate the secondary carbocation. This secondary carbocation will undergo rearrangement. The first rearrangement is the hydride shift to generate a new secondary carbocation, which will further undergo a metal shift to generate a tertiary carbocation. Recall that a tertiary carbocation is more stable than a secondary carbocation because there is more hyperconjugation in a tertiary carbocation as compared to a secondary carbocation. This tertiary carbocation is then trapped by ethanol. It's a neutral molecule, which then gives you the final product. Let's look at some examples where the rearranged carbocation loses a proton to form a carbon-carbon double bond. So this looks like a pretty complex molecule, but let's focus on the OH group right here. This is an alcohol. If you treat this molecule with sulfuric acid and you heat it, it will get protonated, lose a molecule of water, and then form a carbocation. This is a tertiary carbocation. It can form a double bond by losing a proton attached to this carbon atom. But if it loses a proton, this proton, and forms a double bond, the resulting double bond is a trisubstituted alkene. It won't do that. Instead, it will undergo a methyl shift to generate a new tertiary carbocation, which will then lose a proton to give you a double bond. The double bond so formed is a tetrasubstituted alkene, which is more stable than a trisubstituted alkene. Let's look at another example. This is a chloride. If you heat it in presence of para-toluene sulfonic acid, it will generate a secondary carbocation. This secondary carbocation will undergo rearrangement via an alkyl shift to generate a tertiary carbocation. The tertiary carbocation will then lose a proton to generate the alkene. That's a double bond. Thanks for watching.